Is this fine? How's it going, everyone? Yeah, so today I will be speaking about what I did for my final year computer engineering project. So as you can see, I was tasked with making an automatic chess robot that you can play against using your voice. So what I want to achieve today is to break down a seemingly complex system into more manageable components. So what does this thing comprise of? So there are three key subsystems. There is the automatic speech recognition subsystem, the chess engine, and the actual mechanical gantry itself. So let's first dive into the speech recognition subsystem. So what does this involve? It involves three things. So there's voice activity detection, and that's used to determine when I'm actually speaking. Because when I say a move, I say four things. I say the piece type, so knight, queen, king, whatever. Then I say 2, and then the file then rank. So an example would be knight to c4. So the voice activity detection component should detect each individual word. Then those can't just be passed into the classifier, right? They need to be formatted in some way. So I use multi-frequency septual coefficients for that, but I'll dive into that a bit later. And then I pass the features into a neural network, which basically spits out what move you said. So to start, how did I implement the voice activity detection? So it's not too hectic. Basically, I've got an amplitude threshold that's, once that is passed, once the amplitude of the speech signal passes the amplitude threshold, it starts recording. But then you can see over there, can you see my mouse? Yeah, you can, okay. You see over there, it dips below the amplitude threshold. Obviously, the recording shouldn't stop there because I wouldn't have completed saying the move. So I basically just wait and see how long it's been below the amplitude threshold for, and then once it's past that duration, the silence duration threshold, then it stops the recording. So then, once that is done, I've got my clip. So now I want to extract every single word that I said. So I basically do the exact same thing again, but now I just reduce the silence duration threshold, and then you can extract each individual word like that. So then here you can see an example of an extracted audio segment. This is me saying night, and I just add some padding to the start and end of it so that I capture the entire word. But now, this word can't be passed into the neural network. So I first have to extract the multi-frequency septual coefficients. But now, why MFCCs? So multi-frequency septual coefficients are used in speech recognition because they effectively represent the perceptual characteristics of human speech by mimicking how the human ear processes sound. I would not have remembered to say all that. I had to read that. So basically that audio segment that you saw, so me saying the word night, that has to be chopped up into all these tiny little frames, right? Then each one of these frames needs to be converted into the frequency domain. So this frame that you see here, this is the start of me saying night. It looks random, but this you can assume to be periodic because the audio signal is so short. But now you can see that the start of the signal and the end of the signal don't end at 0. So now, because of this discrepancy, that would introduce high frequency components that are not desired. So what you need to do is you need to implement frame windowing. So I use the Hanning window, and basically you just multiply this function by the audio frame, and then you get this result. And then you can see it squeezes the start and the end of the audio signal to 0, which removes the high frequency components. So then, when that happens to a frame, then it's converted into the frequency domain. So now you've got all this frequency information. You've got all these frequency bins. So then what happens is you take all those frequency bins and then you pass it through the mul filter bank. So then that basically takes all the frequencies under there and it sums them up together, and then that forms a coefficient. Then you take all the frequencies under there, sum them up, and so on. And you can see how these ones are a lot taller than these. And that's because over here, you're summing a lot more frequencies. So you have to counteract that by just like reducing all of the amplitudes. Yeah, so then this is how you get your coefficients. And then when you do that for every frame, you get the Mel spectrogram. And then this basically shows your audio signal, but in the Mel scale, yeah. And then, yeah, you take the log of that, and then you got your Mel frequency septural coefficients, yay. Then you can pass those into the neural network, and the neural network I trained, I had to like record thousands of audio samples to train it. That was quite hectic, but yeah, so you pass it through there, and then it spits out the move that you said. Cool. Then there is the chess engine. So there are also 3 key components here. There's the internal board representation and move generation. So that's basically how do you actually represent the board in code. Then there's the evaluation function, which looks at the states of a board and determines like who's in a better position, right? Like is white's position more favorable? Is black's position more favorable? And then there's the search algorithm, and that's what like the AI uses to determine what's the best move to play, because you have to be able to play against this thing, right? Cool. So now some of you might think, what about using 2D arrays? Because I mean, that makes sense. Like a chessboard looks like a 2D array. But yeah, that would be a naive approach, and then you'd have to use all these nested loops, and then it just becomes messy. You could go to 1D arrays, but it's not clean. So I use these things called bitboards. So some of you may have heard of what a bitboard is, but yeah, basically it's a 64-bit number, right? But you visualize it as an 8x8 matrix. So then wherever there's a 1, like whenever a bit is a 1 in this number, then you know a piece is in that position, right? So you see all these 1s in the positions where all the pieces are. But now you're probably wondering, how do you know like what piece is in that position? Okay, like I see a piece is in that position, but like how do I know? So you basically have bitboards for every single piece type and for each color. So yeah, you'll have a bitboard for the rooks, for instance. So this will have a 1 over there, 1 over there, 1 over there, 1 over there. So now you know where all the rooks are. And then you have another bitboard for the white pieces. So this will show you where there is a white piece in a position. So then the cool thing is, because these are just unsigned integers, you can use the AND operation on them. So if you take this bitboard and you AND it with this, then you get the white rooks. So you get the rook bitboard, you AND it with the white bitboard, and you get the white rooks. Pretty simple. So now I want to show you where the true power of bitboards lie. So this is the knight move bitboard. So this shows like all the moves that a knight can possibly make if there weren't any other pieces on the board. And then right now, the king is in check, right? So this shows where you would need, like all the places you could possibly place a white piece in order to stop that check from occurring. Well, yeah, to stop the check. So then you take this bitboard, the knight bitboard, and you take the check mask and you AND them together. And then now you have the legal moves for the knight. So just by using one operation. I mean, calculating all this stuff is another story, but you know, I'm just giving an overview, yeah. But yeah, then here's another example. So right now, this rook is pinned by that rook, right? So now, this rook, if there weren't any other pieces on the board, would be able to move up this column and, yeah, I mean, like, you know, side to side here. But obviously, it can't move up there because then it would leave the king in check. So that's an illegal move. So you take a pin mask, which basically is just all the blocks between a sliding piece and the king. And you like, yeah, so that's that bitboard. And then you just AND it with the pseudo-legal move bitboard for the rook. And then you get all the actual legal moves for the rook. Cool. So now we have the evaluation function. So remember, as I said, the evaluation function is used to determine how strong of a position either side has, given a certain board state. So I used quite a simple one. I didn't come up with all these values myself. I'm not like the greatest chess player. But yeah, so basically there's the piece values and there are the p-square tables. And when I looked at the name of the person who proposed the specific evaluation function, I just knew I could trust him. Okay, so for the piece values, I think like you guys are probably used to a pawn being worth 1, a knight being worth 3, bishop 3, rook 5. But this guy, for some reason, wanted to define the stuff in centipawns. So he valued the bishop slightly more than the knight. Yeah, so these are the values that are used for all the pieces. And then the piece square tables are basically like this map, right? So this one is used for the pawn. So if a pawn is in that position, right, then it isn't given any bonus points because it's like, okay, it's like that position's okay. But now, if you move it up 2, which is a common move to play, then it'll get 25 bonus points. So every single piece is looped over on the board, and the piece value is added to the evaluation, and then the bonus is added to that. So that happens for all the pieces. And then over here on the right-hand side, this is the knight p-square table. So you can see that it favors the knight being more in the center of the board, which makes sense because knights on the edges and in the corners are more weak. They can't really move too many places. Yeah, before I move on to the next thing, so basically all the piece values and all the p-square table bonuses are added together for the white pieces, and then it's added together for the black pieces. Then the black evaluation is subtracted from the white evaluation, and then so basically if that result is positive, then white's position is favored. If the number's more negative, then black's position is favored. So now we've got the evaluation function, but now we actually have to search all the possible moves that can be played, evaluate all of the states, and then basically get the best move. So I used a min-max tree, and I used this because white is the maximizing player, so it always tries to get the highest score or the highest evaluation, and then black's a minimizing player, so it always tries to get the lowest evaluation. So yeah, then this tree is just searched through, and then say I'm playing as white, I want to try to get the highest score, so then I'll like try to search for the highest number. Yeah, and then whatever branch returns the highest value, that move will be played. Well, in this case, it'll be that move. But yeah, then I used alpha beta pruning just to optimize it a bit more, because you don't want to be like searching like every possible move, because that would just take too long. Yeah, then there is the mechanical gantry system. I basically just designed. It's like a glorified 3D printer essentially. Yeah, so I just designed this XY gantry, and then there is a stepper motor over there, and a pulley over there, and another pulley over there, and then those move a belt, and the belt connects to the arm, which you can see over here. Yeah, and then, so yeah, that I can achieve a XY movement with. Then there is the Z-axis movement, so I just have a lead screw there. There's like a little nut that the lead screw screws into, so whenever that turns, it like lifts the entire components up or down. And then to actually pick up the piece, I used an electromagnet. And that electromagnet fits snugly under there. If that's not clear, I'm looking at this thing down there. So the electromagnet fits under there. And then, yeah, I just put a whole bunch of screws on the top of the pieces so that the electromagnet could attract them. And yeah, so that's how it picks them up. But then when I was testing it, it didn't place the pieces in the center of each block every time, right? So it like pick up a piece or place it down, but now it's like kind of not accurate. And then it did it again, and then eventually it just became so inaccurate, the piece was just not on the correct tile anymore. So then what I did to combat that was I cut out these little holes in the bottom of the pieces, and I put these cones on the tile. So it forces the piece to the center of the tile when it places it down every single time. And yeah, that is the final build of the system. So yeah, let me demonstrate this thing. yeah, I'm hoping this works.
Rook to D1.